right? So tensors are the object of multilinear algebra. They have tons of applications. Multilinear algebra sits between linear algebra and nonlinear algebra. And we want to understand symmetries on tensor spaces. And there are two kinds of symmetries. So let's look at d by d by d by d tensors. So we're starting with, let's take a d-fold tensor product. So V is a vector space. My vector space, typical, will be n-dimensional. So in my examples, V will be Cn. Okay, so then this is simply the space of n by n by n by n by n tensors d times. Okay, so that's the space I'm going to be interested in. So on that space, I have continuous symmetries and I have discrete symmetries. I have a continuous symmetry just coming from the general linear group, right? So the general linear group, acts on matrices by left and right multiplication, and same with tensors. But I also have discrete symmetries just permuting the slots, right? So the symmetric group acts, by permuting the slots. And these two symmetries interface in a very, very nice way. So 6.4 in Landsberg's book is titled Decomposing the Space of Tensors as a GLN module, as a module over the general linear group with the help of the symmetric group. Okay, so we're going to use the interplay of these two. Now, as I mentioned, Landsberg was the advisor of Kay and Luke, and he's leading the effort of a program at the new Simons Institute in Berkeley this fall, so there are tons of connections to theoretical computer science and so on and so forth, and he's doing lots and lots and lots of wonderful work. I think the big difference between Landsberg and me, so for him, every vector space does not. Okay. No vector space comes with the basis, and for me, every vector space comes with the basis. Okay, so let's see how it goes. So every Young tableau T pi. So pi is a partition and T pi is a filling of this with the numbers 1 up to n. And maybe I don't even want to know right now the row strict, column strict. I just fill it in any way. So and pi will be a partition of the integer d. This defines a certain operator, which is called a Young symmetrizer. Which I'll call rho sub t pi. Okay, so t pi is one of my yellow thingies over there. Okay, one of my filled partitions. And each of these yellow thingies defines a linear operator from the space of tensors to itself. An endomorphism of tensor space to itself. And the rule is, by the rule, I'm going to say it in words, anti-symmetrize the rows and symmetrize the columns. And that's consistent with the rule I described here, and it's the transpose of the rule in Landsberg's book and used by many people. Okay, so I'm anti-symmetrizing the rows and I'm symmetrizing the columns. So let's do an example. So for example, let's take row sub 1, 2, 3. Okay, so I take this partition of 3 and I fill it like this with the numbers 1, 2, 3. So this is now a linear map that takes a 3-dimensional tensor and turns it into another 3-dimensional tensor. Well, all I need to tell you what it does on a basis tensor, so I might as well look at decomposable tensors of the form A, tensor B, tensor C, an element in the Segre variety, a rank 1 tensor, an independent table, blah, blah, blah. And so what I'm going to do is I'm symmetrizing and anti-symmetrizing. Let me write down the answer, and then you can see what I mean. So first we go A tensor B tensor C plus C tensor B tensor A, right? That's the symmetrization of the columns, right? So in the column I have a 1 and 3. So this says I can swap the first and the third position, and I just have a plus sign. Okay? And then I anti-symmetrize whatever is in positions 1 and 2. So I get a minus B tensor A tensor C minus B tensor C tensor A. Okay? And you think about this for a moment, you realize you can do it in either order. Okay? So either you first anti-symmetrize along the row using the numbers 1, 2, 3 and so on as indices for the slots. Either anti-symmetrize first the rows and then symmetrize the columns, or the other way around. Okay? Well, that's a linear map from the space of tensors to itself with coefficients plus, minus 1 and 0. Okay? Now this linear map has an image. The image of this linear map, so the image of the Young symmetrizer applied to the space of tensors, and take my word, that's an irreducible GLV module. Okay, it's an irreducible. And the isomorphism type depends only on the partition, but not on the filling. Okay? So if I had taken, here I've taken a different filling. So rather than 1, 2, 3, if I had taken 1, 3, 2, I'd have gotten a different linear map, right? And that other linear map has another different image. Right? So here, I'm mapping the n-cubed dimensional space of tensors into a subspace. And the other row would map it into a different subspace. But those subspaces are isomorphic, both as vector spaces and as GLV modules. Okay? So that's the statement. And then this module is called the Schur module. So the Schur module S pi of V is the irreducible GLV module given as the image of a Young symmetrizer that you get by taking pi and filling it into a tableau T pi in some standard way. Okay?
Can you read the multiplicity from this map? How many times it appears?
Yes, we're about to do that. Okay? Now it's indirect. I mean, all of these things, always think about snowboarding. You've got to work it out. You have to practice. Don't just listen, and people tell you how this works. You have to sort of try it, Here's a proposition from Landsberg's book. That's 6, 4, 2, 5. Or is it 6, 4, 25? I think it's 6, 4, 2, 5. Okay? And it says the following: the dimension of this vector space, so the dimension of the Schur module, the rank of this linear map. So we're now given a formula for the rank of this row map. The dimension of the image vector space is a certain combinatorial number. It's the product over all x in the diagram. So I take the product. X is one of the boxes. Okay? So one of the yellow boxes. So take a product over all yellow boxes. And then I take n. So n is the dimension of V. So n is going to be the dimension of my vector space. And then I'm going to add C of x Now divide the whole thing by h of x. So I have to tell you what these things are. And so C is called the content. It's the content of the box in the diagram, in the tableau. And H is called the hook length. Okay, so I will do this for you in an example. I think rather than, giving you the formal definition, I'm going to work out an example, and let me see whether I can get rid of my beauty.
There is no D in this formula.
D is contained in the number of boxes of pi.
Yeah, D is implicit. So D, where's the D?
Pi is a partition.
Oh, pi is a partition of D. Yeah, exactly. So pi, let's record that. Pi, thank you. Pi is a... There's a lot of things going on. So this is kind of a busy scenario. So let's work out one example. And as we go along, I'll tell you what the content and the hook length are. Okay. So the example... so for example, okay, here, so the favorite examples is S d of V and wedge d of V, okay? So those are the symmetric power and the exterior power. So SD is the space of homogeneous polynomials of degree d in V. And sorry, Luke, I'm going to ignore duality. So this is S sub blah 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 of V. So if my partition is simply the partition 1 1 1 1 1 1 1, then, or maybe I want this to be the D. Maybe I want the D partition, right?
You have to,
Maybe
transpose it for this formula to work.
I see. So maybe I want 1 1 1. Okay. Anyway, so I think it's going to work out. Okay, so one of them is the exterior power, the other one is the symmetric power, and these are 2 of the 5 irreducible representations. So let's do the 5 irreducible representations, GLV modules for fixed D of degree D equals 4. Okay? So to answer Kang Jin's question, so I'm fixing D. So D is the degree of the representation. Remember from yesterday, so a representation is a polynomial map that takes a small matrix and eats a small matrix and makes a big matrix. Each entry in that big matrix is a homogeneous polynomial of degree D in the entries of the small matrix. So that's the D. Okay? That's how we get it. Here, so there are 5 irreducible representations of degree 4 irrespective of what n is. For any n, there will be 5 of these. And I'm going to give you this formula in each case. So according to the partitions, so the first partition is like this. Then we have that one. And we have this one. This one. And finally that one. Let me draw it twice. Okay, once for the content and once for the hook length. Okay, so now we're going to do content here and hook length there. Okay, so so the content is a function that assigns a number to each box, and the way I'm going to do this is that at the upper left corner the value will be 0. Okay? And then, think about this sort of as the matrix. So below the diagonal, I'm increasing by 1. 1, 2, 3. And then above the diagonal, I subtract each by 1. So I go, minus 1, 1, 0, minus 1, minus 2, 1. So, okay, it's kind of a triplets, picture. So, and then I go minus 1, minus 2, minus 3. Okay, so C of, if this is the box, right, X in this shape, then C of that X is minus 2. Okay, the hook length goes like this. So it's 4, 3, 2, 1, 4, 1, 2, 1, 3, 2, 2, 1, 4, 2, 1, 1, 4, 3, 2, 1. The hook length is arm plus leg. Okay? So when people draw a partition, so it's sort of, something like this, some big partition like this, and then you have some entry X here, right? And you count the number of boxes to the right in the partition, including X. That's the arm, right? And then you add to it the number of boxes, below. That's the leg. Okay? So if you're a box in the partition, then your arm is you and everybody to your right, and your leg is everything below you, including yourself. Okay? And the total number of boxes in the arm and the leg together, Abraham, is the hook length.
Yeah, the
So
content is how is the filling in the second column?
here so for the content I just take this matrix. So I do sort of the dummy triplets matrix: minus 1, minus 2, minus 3, minus 1, minus 2, minus 1, 1, 1, 1, 1, 1, 2, 3, 2, 4, 3, 2, right? And then you take whatever you get on the partition. Okay? Yeah. So I take the matrix whose entry in row I and column J is J minus I. And then I just put it into my partition. That's called the content. And the hook length is arm plus leg. So for example, here, this box has hook length 4 because the arm has 4 things. 3 things. Maybe I take this out, right? And then it's just, so it's the total number of boxes, not double counting. Okay? I hope I got this right. Okay, so that's the hook length. And now, what are the dimensions? So this one is the symmetric power. So this is, n times n plus 1 times n plus 2 times n plus 3. So this is the numerator, right? And then the corresponding denominator is 4 times 3 times 2 times 1, right? So this product is over all the boxes, right? And then the boxes contribute this quotient, this quotient, this quotient, and that quotient. That's the dimension of SD, the dimension of the space of homogeneous polynomials of degree D homogeneous polynomials of degree 4 in n variables. Agreed? Then here we do exactly the same thing. We go n times n minus 1 times n plus 1 times n plus 2. Right? This comes from the content in the numerator. Everybody sees that? And then I multiply, these hook lengths, so 1 by 1 by 2 by 4. Okay, here again, the content gives me n squared times n minus 1 times n plus 1. And then the hook lengths give me 1 times 2 times 2 times 3. 2 more to go. Content gives me n times n minus 1 times n minus 2 times n plus 1. Hook lengths give 1 times 1 times 1 times 2 times 4. And finally, for the exterior algebra, I get n times n minus 1 times n minus 2 times n minus 3, 1 times 2 times 3 times 4. That's the dimension of the dth, the 4th graded component of the exterior algebra. That's the number of 4-element subsets in an n-element set, also known as n choose 4. Okay? Now, I'm going to show you a miracle. Okay? So that's how this formula works. So now, are you ready for the miracle? Well, let's multiply this by 1. Let's multiply this by 3, by 2, by 3, and by 1. Well, those are the dimensions of the corresponding Specht modules. Okay? These are the dimensions of the Schur modules, which are the irreducible representations of GLN, 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 each indexed by one of the 5 partitions. These are the dimensions of the Specht modules, the irreducible representation of S4. Let's multiply them and then add this up. Okay? So you add these polynomials. Well, these are 5 polynomials in n of degree 4. And if you add them up, you type this all into Sage, you find that this equals n to the 4th. That's a miracle. Okay, everybody clear what I did? So I took this formula, I evaluated 5 times. One for each of the 5 partitions of 4. I get 5 polynomials of degree n. So those are the dimensions of the irreducible representations of degree 4 of an n-dimensional of GLN. Then I just multiply by the corresponding dimensions of the irreducible representation of S4. I add up, I get n to the 4th. And that is explained in a second by Schur-Weil duality. So here is the double commutant theorem. And this is theorem 6451. Okay? So Landsberg's labeling system is a little bit like Wittgenstein's. So then let rho be a representation. So okay, let rho be the natural representation of GLV on the tensor space. Okay, so GLV acts, on the tensor space by simultaneously acting on each slot. Okay? And that rho be the representation of the symmetric. Okay? So everybody in this room now knows how to write down these matrices. Rho is given by a n to the 4th times n to the 4th square matrix. A square matrix of order n to the 4th, whose entries are polynomials of degree d in n squared variables. And you know how to make them. That's what we practiced yesterday. Okay? Is this clear? So rho is a polynomial function of degree d from this n squared dimensional vector space to this, I guess, n to the 8th dimensional vector space if d were 4, as in the example. Okay? And rho, is the permutations, right? So for every permutation of the d slots, you can write that as a permutation matrix, a big matrix, again of order, n to the d by n to the d. Then the following holds. Then psi of SD, so the image matrices, are exactly the matrices upstairs. They're all the big matrices of the big format which commute with the other guys. So G times rho of A equals rho of A times G for every element in the general linear group. Okay? So the upstairs permutation group, the image of the permutation group upstairs, is exactly those big matrices that commute with all the matrices coming from the general linear group, and vice versa. Because it's a double commutant theorem. Rho of GLV, so this is the image of GLV under the representation. So it's the upstairs matrix group of which you've written down a parametric representation. And set of all G, again, set of all big matrices that such that G commutes with psi of sigma for every permutation sigma. Okay, so these two guys perfectly intertwine, right? So one group is exactly the guys that commute with the other. Now, I'm not going to say anything about the proofs, right? For one thing, we only have, 55 more minutes and lots of things to cover. But also, this is an introduction to nonlinear algebra. It's kind of an applied course. I mean, I want you to learn these, get a flavor of these techniques, and see how you can use them to carry out calculations. In a more formal, pure math course, you would spend an entire semester deriving and proving these things, probably not just for GLV, but an arbitrary Lie type. And people teach and take classes on Lie theory, and they study these things systematically. So Schur-Weil duality. So that's the theorem that explains this miracle. And this is 6, 4, 5, 2. It says the following. The irreducible decomposition of tensor space as a module over the product of the two groups, as an SD times GLV module, is the following. So V to the D is the direct sum over all partitions pi of D of the tensor product bracket pi and S pi of V. And there's more coming, but let's look at this equation first. Okay? So what? Pardon me?
What means?
I'll explain everything. Okay? So V tensor D is a vector space, is our tensor space of dimension n to the d. Okay? So that vector space is a direct sum of a bunch of other vector spaces, one for each partition. One for each of the 5 partitions of 4, there's another vector space. That vector space is the direct product of the Specht module and the Schur module. So this bracket pi is the irreducible representation of SD indexed by pi. So that is the vector space whose bases are the yellow filled, tableau from 35 minutes ago. That's that vector space. The tensor and that vector space has these yellow dimensions. Okay? Let's make it yellow. Okay? Then I take the tensor product with the Schur module. The Schur module I also described. That's a vector space that has this dimensions. Well, just as vector spaces, right? This dimension is n to the 4th. That's an n to the d dimensional vector space. Right? So just at the level of these dimensions, this is the miracle. Okay? So my miracle says that the dimension of this vector space is the sum of the products of these dimensions. And the dimension of a tensor product of two vector space is the product of the dimensions. Okay? Now furthermore, this explains the action and this double commutant. So this part carries the SD, the symmetric group action, and this part carries the GLV action. Okay? So there exists a change of basis in tensor space, so you can write like this. Now notice, by the way, that in this interpretation it is multiplicity free, right? So each of these direct products are the irreducible representations of this group, and each of these irreducible representations occurs with multiplicity 1. Okay? But now, as a sort of corollary, hence, the isotypic decomposition, and that's the one we're often most interested in, just as a GLV module. So we're forgetting the SD part, can be written like this. So again, V tensor D, or tensor space, is the direct sum over all partitions pi of D of the Schur module. But now each Schur module occurs some certain number of times, namely the number of standard tableaux of shape pi. Right? So the dimension of pi. Okay? So I'm sort of, naming them all differently, and here I'm aggregating them all together. I disregard the action of the symmetric. Okay? That's Schur-Weil duality. Okay, I know this is tough, but it's going to get tougher. Okay? So now what we're going to do, we've decomposed the space of tensors. That's nice. But we want to do better, right? We want to study polynomial functions on tensors. We're not only interested in tensors, but we're interested in spaces of polynomial functions on tensors. And that's section 6.5. 6.5 is called decomposing SD of A1 tensor A2 blah 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 tensor AN. Did you get your book back, by the way? Yeah. So if anybody wants to look at it later, so this is the title of 6.5 as a G module, where G is GLA1 tensor, I guess direct product, huh? Direct product GLAN module. Okay. Now what on earth are we doing? Okay. So now we're going to change the group. Okay. Then we will take a direct product. So these A's are vector spaces of different dimensions. I just take a bunch of vector spaces of different dimensions, 2, 3, 5, and 7. Okay. So then this tensor product is the space of 2 by 3 by 5 by 7 tensors. Now I look at polynomial functions of degree D in the entries of a 2 by 3 by 5 by 7 tensors. That's that space. Okay? So I'm interested in talking about polynomial functions on these tensors. Okay? That's a very interesting vector space. We want to understand functions. We want to understand the geometry of tensors. We want to talk about polynomials that vanish on certain tensors. Okay? That vector space, like all vector spaces I have ever met, comes with a distinguished basis, right? The monomials of degree D in the entries of this tensor. Statistics, these are the raw probabilities, right? So this comes with the basis. But that basis can and should be changed to another basis according to the combinatorics we discussed. So that's the content of 6.5. a new basis that has better properties with respect to the general linear group. The group of 2 by 2 matrices acts 3 by 3, 5 by 5, 7 by 7 acts on different sides of the tensor in a natural way. Okay, by left multiplication, right multiplication, up multiplication, under multiplication, side multiplication, whatever you want to think about in tensor space. Okay? So to apply sure-while duality to this situation, what we're going to do is we're going to start with our tensor space. This is going to get quite sneaky now. And we're going to apply sure-while duality as follows. Okay, we're going to look at V tensor D. So V is already a space of tensors, and we take, the default tensor power of that space. Okay, that's a big tensor space, right? So we already have a space of tensors, and then we take, call that, space of tensors Joe. Okay, and then we take Joe, tensor Joe, tensor Joe, tensor Joe. Right? So now we have a really high-dimensional tensor. Okay. So that decomposes in the following way. Well, as A1 tensor D tensor A2 tensor D blah 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 tensor AN tensor D. Right? That's simply just the tensor multiplication is commutative and associative. Right? That's the isomorphism. I'm going to be careful. So A tensor B is isomorphic to B tensor A. And A tensor B parenthesized tensor C is isomorphic to A tensor parenthesized B tensor C. Okay, so there's an isomorphism. Okay, now in each factor we can apply sure-while duality. So in the first factor we're going to apply this formula. So this is the direct sum. Maybe I'll do this over here so we have a little more space. So we're going to continue over there. This is equal to the direct sum. Pi 1 is a partition of D. Specht module pi 1 times sure module S pi 1 of A1. Tensor product, blah, blah, blah. So we do this for each of the factors, and then the last factor is pi n, some other partition of D, corresponding Specht module, tensor product, corresponding sure module. So we're using this middle decomposition n times. Okay. Now again, we're going to regroup terms. So we're going to write this as direct sum over n tuples of partitions. Pi 1, pi 2, up to pi n. All of these things are partitions. And now, this is just to think about this as a tensor product of vector spaces. So we can pull all the Specht modules out. So pi 1 tensor, pi 2, blah, 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 pi n. And we put all the sure modules on the other side. So this is S, pi 1, A1, blah, 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 S, pi n, AN. Okay, so that's just another way of writing this big tensor space. But now we're going to note that SDV is the set of symmetric tensors. that are invariant under permuting slots. But that's something we've heard many times in the last couple of weeks, right? A polynomial homogeneous of degree d is the same thing as a symmetric tensor. So we heard that in Alina's talk. We heard that many times, that symmetric tensors are the same thing as polynomials, right? So we're realizing now polynomials as those tensors that are invariant with respect to our discrete symmetry group. We get the following corollary. The proposition 6, 5, 12 has a G module, the space of polynomial functions on tensor space is the direct sum over partitions pi 1, pi n, all partitions of D, of S pi 1, A1, tensor blah blah blah, S pi n, an, and then this occurs a certain number of times. And the number of times this occurs is the dimension of invariance in pi 1 times pi n. Okay. Well, that's it, right? We've derived that. Okay? So pi 1 tensor pi n is a representation of SD. And I've given you the matrices, guys. I've given you the matrices. You just take the tensor product or Kronecker product of the little 2x2 and 3x3 matrices I've given you, right? So Vissarion has a bunch of partitions: 2, 2, 3, 1, 2, 2, 4, 4, 1, 1, 1, 1, 1, 2, 2, right? I just tensor together my matrices, and then I calculate how many vectors in that space are left invariant by all 24 matrices, the number of fixed points. Okay? That's it. That's an integer, and that's the decomposition of the space of polynomials into invariants that underlies all the recent progress that we've seen in this area, some of which I'll come back to. Okay? Let's see some examples and then take the break, second break. So 652 is the two-factor case. It's a spaces of matrices. Okay? How should you write polynomial functions on the space of matrices? Even that might be unfamiliar. For example, so space of matrices is SD A1 tensor A2. Okay, so if you want to study, 4x6 matrices, so think about this as a 4-dimensional vector space, that's a 6-dimensional vector space, and we're interested in homogeneous polynomials of degree 7. So we're interested in homogeneous polynomials of degree 7 in 24 unknowns. The entry is over 4x6 matrix, and we want to rewrite it in a way that respects the action of GL4 and the action of GL6. Okay, so this formula above there can be written like this. I take partitions of D, S pi A1 tensor S pi of A2, and it's multiplicity free. So it turns out in the special case where n is equal to 2, the following happens. This number, the yellow number, is either 0 or 1. And it's 1 if the two pi's are the same, and it's 0 if they're different. That's all. These yellow numbers are either 0 or 1, and they're exactly 1 if they're the same, so I can rewrite this. That's how it goes. So for example, quadrics, or d equals 2, quadrics on matrix space. So S2, so let's say we're in the space of m by n matrices, okay? So this can be, actually I want to maybe do this over here, and then we'll take the break. So there are two factors, right? So there are two partitions, this one and that one. For d equals 2, there are only two partitions, so there's S2, Cm, tensor product, S2, C2, and then the other factor is S wedge, 2, Cm, wedge 2, Cn. Okay? And what are the dimensions? Well, this one, right, again by hook length, has dimension m times n plus 1 over 2 for this one, and then n times n plus 1 over 2 for that one. And then from the exterior product, we have m times n minus 1 over 2, the number of two-element subsets of an m-element set, and then n times n minus 1 over 2. You add them up, miracle, we get mn times mn plus 1 over 2, which is the space of quadratic polynomials, functions on matrix space. So I had one more example, but I think you're exhausted. You need a 4-minute break, 240-second break. So this is just at the level of dimensions. So if you have a quadratic polynomial on a space of matrices, you've got to break up that quadratic polynomial as a sum of two invariant polynomials. It's a bit painful to do. Finding the bases is a bit of an art, requires some practice. So Luke has perfected that, and we can all learn, from Luke how to do this. But if you have a computational problem that has invariant structure, this is the difference between being able to do it and not being able to do it. I'll see you in 4 minutes.